Hello, and welcome to Lesson 4.7, Optimization Problems. This section is just a collection of word problems, basically, that we are going to be using the techniques we learned in the previous sections in Chapter 4 on maximizing and minimizing functions. We're going to be using those in context and application problems. These are different from related rates problems in that we're not going to be using implicit differentiation. We're going to actually be finding a function, an explicit function of one variable, and then using first derivative test or second derivative test to find where those functions are maximized or minimized. Examples about a farmer that wants to fence in an area of 1.5 million square feet in a rectangular field. So we have a rectangle and then divide it in half with the fence parallel to one of the sides of the rectangle. How can he do this so as to minimize the cost of the fence? So we see why this is an application of max and mins, right? We want to minimize the cost. So the first step, figure out what you're being asked for. So we're being asked for the least cost. Now notice that we're not given any costs, any dollar amounts for different sides of the fence. So we can assume that all the fence costs the same. We also need to remember that we have some constraints that the fencing is going to fence an area of 1.5 million square feet. We're going to have this. So we're thinking about the perimeter of the fence because that's the amount of fencing, right? And so if we minimize the perimeter, we're going to minimize the cost if all parts of the fence cost the same. Step 3, we want to give some symbols to assign. So since we want to minimize the cost, and it's really minimizing the perimeter plus this one side, what we want to do is assign symbols to the different sides. So we have 3 parallel sides, and we'll call those X, going one way, and then 2 parallel sides going the other way, we'll call those Y. So how much fencing do we need? Y plus Y, which is 2Y, plus 3X. So that's how much fencing we need. So let's call that P for perimeter, plus that guy thrown in there. So moving on to step 4, we want to minimize this function. That's the amount of fencing we're going to need in terms of those parallel sides. And we need to remember that we need to keep it at the area, which is X times Y, at 1.5 million square feet. So since this is a function of 2 variables, and we have this other relation here, we can get one of these variables in terms of the other because we're going to need a function of just one variable. If you think about it, all our problems that we've done up to now have been functions of one variable, unless we're using implicit differentiation. So I'm going to solve for y in this expression for area and replace this y in my perimeter function. And so I get P of x equals 3x plus 3 million over x. So we have our perimeter in terms of one variable. And now we need to think about what we need to do. We need to find the minimum value of x, the value of x that minimizes that function. So what are the ways that we have found that? So we've used the first derivative test, we've used the second derivative test, and we've used the closed interval method. It all comes down to really finding the critical values and then knowing whether to interpret them as a maximum or a minimum. And remember, if you have a closed interval, you also need to check the endpoints. So we need to figure out what our domain is that we're dealing with in context here. So, x is going to be greater than 0. That's a given. But we're not really given any upper limit on x. Practically speaking, it's pretty silly to have a rectangular area that's 1.5 million square feet long and 1.5 million feet long and 1 foot wide, but you know, this problem's not telling us we can't have that. So we don't have any upper limits on x, so we're just going to assume that x is greater than 0. So we don't have a closed interval. So now we're going to go and use our methods to find the critical values. So we take the derivative of p and we find the zeros of that, so our critical number occurs at x equals 1,000. So now I'm going to go check and see if that's a maximum or a minimum. And since I don't have a closed interval, I'm going to just use the second derivative test here. And when I take the second derivative, I get 6 million over x cubed. And now that's always positive because x is always positive. So the second derivative test tells me that p has a local minimum at x equals 1,000. So the farmer should make the 3 parallel sides 1,000 feet. And then when we solve for these other 2 sides, we use that area relation. We get y equals 1,500 feet.